The company that builds more batteries than anyone else on Earth just put its weight behind a material most of the industry had written off years ago. Not a rare metal, not some lab-grown compound nobody's heard of. Sodium, the same element sitting in your kitchen salt shaker right now. CATL is the world's largest battery manufacturer, the company already supplying a huge share of the electric cars on the road today. And the material at the center of its newest battery line is so plain, so cheap, and so unremarkable that when you hear what it is, you'll probably laugh. A battery built around table salt just became one of the biggest stories in energy. And getting here took 30 years of science, billions of dollars in bets, and one material problem that stumped researchers for 4 decades straight. By the end of this, you'll understand why lithium took over everything in the first place, why the world is finally circling back to an element it walked away from 60 years ago, and why something sitting quietly in your kitchen might turn out to be one of the more important materials in the next decade of energy. Car makers have a simple reason to care about all of this. Battery packs are still the single most expensive part of building an electric vehicle, and shaving even a small percentage off that cost can be the difference between a car that sells and one that sits on a lot. That's part of why automakers had already been hunting for cheaper lithium chemistries for years before sodium ever entered the conversation. To understand why a salt battery matters this much, you first have to understand how completely lithium took over the world before it. Before lithium batteries went mainstream in the early 1990s, portable power was heavy, bulky, and short-lived. A camcorder battery lasted about an hour. Laptops were thick slabs that barely made it through a meeting. A phone that fit in your pocket and ran all day sounded like science fiction. The older batteries powering all of that stored a fraction of the energy lithium could hold and weighed far more doing it. The jump to lithium wasn't a small step forward. Energy storage roughly tripled compared to what came before. Devices shrank. Phones got smart. Electric cars went from a concept to a real product on real roads. Wireless earbuds, laptops thin enough to slide into a sleeve, EVs humming down the highway. None of it happens without lithium chemistry making it possible first. Lithium earned that dominance because of 2 things working together. Lithium particles are among the smallest and lightest of any element used in battery chemistry, so you can pack an enormous number of them into a small space, which means more energy stored per kilogram. And lithium has a strong natural pull to push electricity through a circuit. Put those 2 properties together, and for 30 years, nothing else came close to competing with it. So the world built everything on top of it. Factories scaled up. Billions of dollars flowed in. Researchers spent decades fine-tuning the same core chemistry instead of looking for a replacement. When one approach works that well for that long, an entire industry stops asking whether something better might be sitting nearby. And that's usually right around when the cracks start showing. In 2016, Samsung released a flagship phone called the Galaxy Note 7. The reviews were strong, pre-orders poured in. Then within weeks, the phone started catching fire in pockets, on airplane seats, on nightstands while people slept. Airlines banned the device outright. Samsung pulled the entire product line, a recall that cost the company roughly $5 billion and became one of the most talked about product failures in consumer electronics history. Most people blame Samsung, and Samsung did make specific design mistakes with that particular battery, but the danger underneath it was never unique to that one phone. It was sitting quietly inside every lithium battery ever built. The liquid that carries energy back and forth inside a lithium cell is flammable, genuinely combustible under the wrong conditions. Overheat it, puncture it, or charge it too aggressively, and that liquid can ignite. Once one cell catches fire, the heat raises the temperature of every cell packed next to it. And those catch too, spreading through a sealed battery pack faster than most cooling systems can respond. Engineers have technical language for that chain reaction. Everyone else just calls it a fire that shouldn't be happening in someone's pocket. Cold weather causes a separate problem, one that's just as real and gets far less attention. When temperatures drop below freezing, the charged particles inside a lithium cell stop moving smoothly and start building up on the inner walls of the cell as tiny metallic spikes. Grow long enough, and one of those spikes can bridge the two ends of the battery and cause a short circuit, which generates heat fast, and heat inside a lithium battery tends to move in one direction only. Even short of that failure, the performance hit from cold alone is real. Independent testing has repeatedly found electric vehicles losing well over a quarter of their range in freezing conditions, sometimes closer to a third, not because anything broke, just because the temperature outside dropped. For an EV owner in Minnesota, Maine, or anywhere winter actually shows up, that's not a minor inconvenience. That's the difference between making it home and not. Engineers have known about both problems for years. They built smarter thermal management systems and better battery software around them, but the core chemistry never changed. And underneath both of those problems sat a third one that had nothing to do with engineering at all. Between 2021 and 2022, the price of the key lithium raw material climbed several times over in less than 2 years. Then, in 2023, the market reversed hard, giving back most of those gains within a single year. Car companies trying to hit price targets and governments trying to build energy independence around electric vehicles were building their entire strategy on top of a material that swung in price like a commodity nobody could actually predict. That volatility, more than the fires or the cold weather, was the moment a lot of serious people in the industry started looking for an alternative that didn't come with the same baggage. That hunt already reshaped the EV market once before sodium showed up. Over the last several years, a growing share of new electric vehicles, including some of Tesla's own standard range models, quietly switched to a lithium iron phosphate chemistry instead of the higher-density lithium formulas used in premium long-range cars. It's cheaper, safer, and less dependent on some of the most expensive raw materials in a traditional lithium pack. That shift proved something important. Automakers were already willing to trade a little range and energy density for a lower price and a safer battery, long before anyone outside a research lab was talking seriously about sodium. Sodium is really just the next, more extreme version of that same trade. It turned out the answer had been sitting in old research papers for decades, waiting for a reason to matter. Long before lithium was on anyone's radar, scientists in the 1960s were already exploring a different element as the future of batteries: sodium. It sits directly below lithium on the periodic table, behaves in a chemically similar way, and is one of the most abundant elements on Earth. It's in the ocean. It's in the ground almost everywhere. It's in the salt shaker on your table. Ford Motor Company built one of the first high-energy rechargeable batteries around sodium back in the 1960s, and it genuinely worked as a proof of concept. But it needed an operating temperature of roughly 300 degrees Celsius to function, hot enough to melt lead. Fascinating in a lab, useless under the hood of a family car. Then, in 1972, a researcher named Stanley Whittingham figured out how to make a lithium battery work at room temperature, work that later earned him a share of the Nobel Prize. Lithium leaped ahead in that single moment, and nearly all the world's battery research money followed it. By the time Sony launched the first commercial lithium battery in 1991, the direction was locked in. Over the following decades, well over $1 trillion flowed into lithium technology. Sodium sat on a shelf, not because anyone proved it was worse at the core chemistry, but because all the momentum, all the funding, and all the factories were already pointed somewhere else. Sodium also had a real technical problem standing in its way, separate from momentum. Sodium particles run roughly a third bigger than lithium particles. Inside a battery, those particles have to slide in and out of a storage material thousands of times without wrecking it. Lithium storage material, a form of carbon called graphite, is built from evenly spaced, perfectly stacked layers, and lithium particles fit between those layers the way a key fits a lock, clean and precise, cycle after cycle. Sodium particles are simply too big for that lock. Every time one forced its way in, it pushed the layers apart and permanently bent the structure. After a few hundred charge cycles, the battery degraded into something basically useless. That single mismatch kept sodium out of serious commercial consideration for more than 40 years. Researchers kept publishing papers, but nobody could find a storage material sodium could actually live inside without slowly destroying it. Then a group of researchers, including a team working in Canada, landed on something that looked nothing like ordinary graphite. Instead of a neat, orderly stack, this material, called hard carbon, comes out of the manufacturing process in a permanently irregular arrangement made by heating organic material, like plant waste, or agricultural byproducts to extreme temperatures inside a sealed, oxygen-free container. The result is a dense structure full of oddly shaped internal gaps, no neat layers to bend or break. Just enough disorganized space to comfortably hold a sodium particle without damaging it over thousands of cycles. For the first time in 40 years, sodium had a material it could actually work with. A lab discovery and a product ready for mass production are two very different things, though. Hard carbon's irregular structure, the very thing that makes it useful, also makes it porous enough to soak up moisture like a sponge, and even a small amount of water inside a battery cell reacts with the liquid electrolyte and slowly destroys the cell from within. Managing that at the scale of a single lab sample is one challenge. Managing it across millions of battery cells built for cars and power grids is a completely different level of problem, and it's the level of problem CATL decided to take on directly. CATL committed years of sustained investment, reportedly running into the hundreds of millions of dollars, to turn hard carbon from a promising lab finding into something it could actually manufacture at scale. Their engineers reworked the surface chemistry of the material itself, replacing the parts that naturally attracted and held onto water with compounds that repel it instead. They also learned to control the size of those internal gaps with extraordinary precision during manufacturing. Too small, and sodium particles can't move in and out efficiently enough to store useful energy. Too large, and you're wasting space that could be holding more charge. Getting that balance right and repeating it consistently across a product built by the millions took years. Most companies weren't willing to spend. Scaling any new battery chemistry from a lab sample to a factory line means solving problems that have nothing to do with the core chemistry at all. How to coat the material onto a thin foil at high speed without defects, how to keep every cell in a batch performing identically, how to catch the one flawed cell in a million before it ships. CATL already runs some of the largest lithium battery factories on the planet, and it leaned on that manufacturing experience directly, adapting existing production lines instead of building sodium manufacturing from scratch. That head start, as much as the chemistry breakthrough itself, is a big part of why CATL got a workable sodium battery to market years ahead of smaller competitors chasing the same idea. The result is a sodium-ion battery line CATL has branded Naxtra, and the performance is genuinely competitive with the lithium chemistry it's meant to sit alongside. Sodium-ion cells hold up far better in the cold than lithium does, since the chemistry inside them doesn't slow down or turn brittle the same way at low temperatures. They're built from materials that don't carry the same fire risk as a lithium cell's flammable liquid core. And because the raw material is sodium, instead of a metal concentrated in a handful of countries, the cost per unit of stored energy comes in well below a typical lithium cell, without the same exposure to a single volatile commodity market. For the average car buyer, the clearest way this could show up is at the low end of the EV market. The segment automakers have struggled hardest to make profitable. A gas-powered compact car has always undercut an electric one on sticker price, mostly because of what the battery costs to build. A meaningfully cheaper battery chemistry doesn't just pad a company's margin. It's the kind of change that can pull an electric vehicle's price down close enough to a comparable gas car that the decision stops being about ideology and starts being about which one costs less to drive off the lot. Here's the part worth sitting with, though. Does this mean lithium is finished? The honest answer is more interesting than a simple yes or no. Sodium-ion batteries carry one limitation they probably can't fully escape, and it comes straight from physics. Because sodium particles are heavier and larger than lithium particles, there's a hard ceiling on how much energy you can pack into a given weight. For an electric aircraft, where every extra gram directly costs range and payload, that ceiling matters enormously. For a phone or a laptop, where the battery has to squeeze into a device with almost no spare room, lithium is likely to stay the better choice for a long time yet. What CATL is actually building toward isn't a story where one chemistry defeats the other. It's a partnership between two chemistries, each doing the job it's genuinely suited for. The company has already built electric vehicle battery packs that split storage across two separate zones. one sodium, one lithium, managed by software in real time. On a freezing morning, when lithium cells are struggling to deliver full performance, the sodium zone can carry more of the load. On a long highway drive, where maximum range matters most, lithium takes over. Neither chemistry gets pushed past what it's actually good at, and the car performs better than either one could manage alone. Think of it less like swapping one battery for another, and more like a thermostat quietly deciding which system handles the moment. Software inside the pack tracks temperature, driving conditions, and how much range is actually needed, and shifts the load between the two chemistries without the driver ever noticing a handoff happened. The car simply performs like it's running on one very good battery, when really it's running on two, each covering for the other's weak spot. This story isn't only playing out in China either. In Michigan, a company called Natron Energy has been building sodium-ion batteries of its own, aimed less at passenger cars and more at the kind of steady, high-power backup that data centers and industrial facilities need. The exact niche where sodium's weight disadvantage barely matters and its safety and cost advantages matter a lot. American manufacturers don't want to sit out a shift this size, especially one built around a material the country doesn't have to import from anywhere in particular. Sodium doesn't run through the same handful of mines and refineries lithium does. It comes out of the ground and out of the ocean almost everywhere, which means a supply chain built around it answers to a lot fewer outside decisions than one built around lithium ever has. CATL isn't alone in making this bet either. Several other major battery makers across China and Europe have announced their own sodium-ion programs over the past few years, treating it less like a lab experiment and more like the next real category of battery worth building factories for. Step back, and the timing here says something worth remembering. The hard carbon research that unlocked sodium's biggest weakness dates back over 2 decades. The science sat quietly in academic journals long before anyone treated it as a business. Serious investment didn't surge towards sodium until lithium's price swings and safety headlines made the case impossible to ignore anymore. The problems with lithium were never hidden. Engineers had documented the fire risk, the cold weather limits, and the supply chain concentration for years. But when a dominant technology keeps delivering good enough results and the profits keep flowing, an entire industry can develop a strong habit of not looking very hard for something better. Change needs a reason bigger than the comfort of staying the same, and lithium eventually supplied that reason itself by becoming too expensive, too unpredictable, and too concentrated in too few hands to keep ignoring the alternative, sitting quietly one row below it on the periodic table. None of the individual pieces of this story are new. Sodium chemistry, hard carbon, none of it required some sudden scientific miracle nobody saw coming. What changed was which problem the industry was finally willing to spend real money to solve. It's the kind of shift that never announces itself with a headline the first time it happens. It just sits in a lab, in a battery pack, in a factory line, quietly getting better until one day it's sitting under the hood of the car in your driveway. The future of a meaningful slice of the energy world was sitting in your salt shaker the entire time, waiting for lithium to get expensive enough for anyone to notice. If a sodium-ion electric car cost meaningfully less than a lithium one and handled winter mornings better, would you buy it? Tell us in the comments. If this video gave you something new to think about, the like button is right there, and subscribing means you'll be here for the next one.